You are about to hear something that identifies the first definitive chemical signature of a world that breathes. Researchers at NASA and the Canadian Space Agency are visibly explaining how the James Webb Space Telescope has successfully pierced the thick, hazy shroud of K2-18b, a Haitian world located 120 light-years away. This digital reconstruction of the planet's atmosphere reveals a cocktail of methane and carbon dioxide, but the scientific disruption occurs with the detection of a molecule called dimethyl sulfide, or DMS. On Earth, this specific chemical is only produced by life, specifically by phytoplankton in our oceans. Researchers contrast the expectation of a sterile, hydrogen-rich environment against the discovery of a secondary atmosphere that suggests a liquid water ocean hiding beneath the gas. A measurable recalculation suggests that the concentration of these carbon-bearing molecules is consistent with a world covered in a global sea, potentially warmed by its red dwarf sun to the perfect temperature for biology. Every new simulation introduces a measurable contradiction concerning whether the intense radiation from a red dwarf would strip this atmosphere away, or if the planet's magnetic field is strong enough to shield a burgeoning ecosystem. Deeper implications suggest that we are no longer asking if life exists elsewhere, but rather how soon we can confirm the presence of this biological exhaust on worlds beyond our own. Could this detection in the K2-18b atmosphere be the final proof that the recipe for life is a universal constant? We invite a calm investigation into these atmospheric findings as Webb turns its golden mirrors toward even more distant super-Earths in the search for a second home. The James Webb Space Telescope recently detected significant traces of methane and carbon dioxide within K2-18b. This distant exoplanet orbits a cool red dwarf star located about 120 light-years. NASA astronomers utilize spectroscopic analysis to identify specific chemical signatures hidden deep within the alien atmosphere. Light from the host star passes through the gaseous envelope, while the telescope records tiny fluctuations. These specific readings suggest the presence of a vast ocean, potentially covering the entire planetary surface. The atmosphere contains a rare molecule called dimethyl sulfide, which often originates from biological life on Earth. While this finding remains unconfirmed, it sparks deep curiosity about the chemical composition of distant aquatic worlds. Understanding these far reaches of space requires immense patience and the steady gaze of our most advanced instruments. You are observing a world that exists far beyond our own solar system in the silent dark. If you enjoy these deep explorations in space, consider subscribing or hitting the like button. It really helps the channel grow and allows me to make content like this. To understand the distance to this world, imagine walking at a steady pace for 1,000 years. Even then, you would not have left the thin shell of our own atmosphere in this vastness. If the sun were the size of a door, the Earth would be the size of a nickel. K2-18b would be a slightly larger coin, perhaps a $50, orbiting a smaller, dimmer light nearby. On this planet, the gravity would pull at your feet with a gentle but insistent weight, making every step feel deliberate. You would feel the thickness of the air, a heavy blanket that holds the heat of the red sun. Think of the way a humid summer evening feels as the sun dips below the trees. holding the warmth in the grass. This planet may possess an ocean so deep that the bottom is made of high-pressure ice, a phase of water unknown to our shores. It is a world of water, not like a glass of ice, but like a deep, still pool at midnight. The scale of this place is large, yet it is made of the same atoms found in a breath of wind. Carbon, hydrogen, oxygen, the building blocks of a simple raindrop, are the same blocks building an alien sea. We find kinship in the chemistry, a shared language written in the periodic table of the elements. When you consider the vastness of K2-18b, you are not looking at a celestial abstraction, but at a physical entity that obeys the same laws of gravity and thermodynamics that govern your own backyard. If you were to drop a stone into this alien ocean, assuming there were a stone to be found, it would sink with the same predictable acceleration you would observe at a local pier. This universality is the tether that keeps us from drifting too far into the unknown. We are exploring a world that, despite its distance, is built from the familiar materials of our own existence. The concept of a Hycean world invites us to recalibrate our understanding of planetary anatomy. On Earth, our oceans are thin films, barely a scratch on the surface of a massive rock. But on K2-18b, the water is not merely a feature, it is a fundamental layer. Imagine a sea that does not end at a few miles of depth, but extends down for hundreds of kilometers. At these depths, the weight of the water above becomes so immense that the molecules are forced into new arrangements. Scientists theorize the existence of Ice 7 or Ice X, exotic forms of solid water that remain crystalline even at high temperatures because of the sheer crushing force of the overhead mass. This is not the cold ice of a winter pond, but a hot, dense mineral of water, a foundation for a sea that has no bottom in the way we understand it. To visualize the scale of this planet, think of the time it takes for a storm to pass over your house. On Earth, a large weather system might take a day to clear the horizon. On a world like K2-18b, with its massive circumference, the storms are grander, slower movements. A single bank of clouds might span thousands of miles, drifting like a silent continent across the dark expanse of the global ocean. Because the planet is so large, the horizon is further away, giving a sense of endlessness to the view. If you were floating on the surface, the sky would feel higher, the air heavier, and the sense of isolation more profound. Yet, even in that vastness, the light from the red dwarf star provides a constant, rhythmic presence, a reminder that this world is part of a system, a cog in the clockwork of the galaxy. The atmosphere of K2-18b is dominated by hydrogen, the most abundant and ancient element in the universe. Hydrogen is the fuel of stars and the primary component of the great nebulae where planets are born. On Earth, hydrogen is fleeting, escaping into space because our gravity is too weak to hold it. But K2-18b is a giant, 8 times more massive than our home, with a grip strong enough to retain this primordial gas. This creates an insulating blanket that keeps the world warm, even though its star is much cooler than our Sunday. This is a quiet form of cosmic luck, a planet positioned just far enough to stay liquid, but massive enough to stay shrouded. It is a world that has kept its original inheritance from the dawn of its solar system. As we look deeper into the chemical signatures, we find carbon dioxide and methane playing a delicate game of thermal regulation. These gases act like a thermostat, trapping heat and circulating it through the thick air. You can think of it as a global greenhouse, but one that has been running for billions of years without human interference. There is a sense of safety in this longevity. The climate of K2-18b is likely very stable, protected by its thick atmosphere and the steady, low-energy output of its red dwarf star. Unlike the erratic flares of younger stars, a mature red dwarf like K2-18 is a predictable provider. It offers a slow, steady glow that doesn't change for eons, allowing the planet to settle into a deep chemical equilibrium. The absence of land on K2-18b changes everything about how the planet functions. On Earth, continents disrupt the flow of ocean currents and winds, creating complex weather patterns and diverse climates. Without land, the winds of K2-18b can travel unimpeded around the entire globe. This creates a more uniform environment where the temperature and humidity are balanced across vast distances. It is a world of smooth transitions, where one region fades into the next without the sharp boundaries of coastlines or mountain ranges. This lack of friction leads to a sense of planetary scale harmony, a world that is essentially one giant, interconnected system of fluid and gas. In our own lives, we measure time in seconds, minutes, and hours. But to understand K2-18b, we must think in the time frames of the star. A red dwarf can live for trillions of years, long enough for the entire history of the Earth to happen many times over. The planet has likely been in its current state for twice as long as the Earth has existed. This means the chemical cycles we are observing, the methane, the carbon dioxide, the water vapor, have had plenty of time to reach a state of perfection. The universe is not in a hurry. The molecules in that distant air are not rushing to become something else. They are participating in a story that has been told for 5 billion years and will continue for 50 billion more. When we talk about the search for life on such a world, we must do so with a calm and patient heart. The presence of dimethyl sulfide, if confirmed, would be a curious data point, but it is not a smoking gun. In the world of science, a single observation is just an invitation for more questions. We do not need to leap to conclusions to feel the weight of the discovery. The mere possibility that a biological process could be happening under that thick hydrogen sky is enough to change our perspective. It reminds us that the conditions for complexity are not unique to Earth. The recipe for life, water, energy, and the right chemistry might be a common occurrence in the vast kitchen of the cosmos. Consider the journey of the data itself. A photon leaves the surface of the red dwarf, bounces off a molecule of methane in the planet's air, and then travels for 120 years through the freezing void. It passes through the outer reaches of our solar system, enters the golden eye of the James Webb Space Telescope, and is converted into a digital signal. That signal is then processed by computers and interpreted by minds on Earth. You are at the end of a long chain of cosmic transmission. The information you are contemplating is a message from the past, a postcard from a world that existed over a century ago. This delay is a natural part of the interstellar conversation. We are always looking back in time to see the truth of our surroundings. The human-scale perspective allows us to bridge the gap between our small lives and these gargantuan distances. If you were to walk along a beach on Earth, you might see the tide coming in and out, driven by our moon. On K2-18b, There is no large moon to create such dramatic tides, but the gravitational pull of the host star is much stronger due to the planet's proximity. The entire ocean might bulge toward the star, creating a permanent high tide on one side of the planet. This slow gravitational massage keeps the interior of the planet warm, contributing to the volcanic activity that might release the very gases we detect. It is a self-sustaining loop of energy and matter, a world that powers itself through its own motion. The pressure on this planet would be immense, creating conditions that differ greatly from our familiar home. Scientists describe this category of planet as a Hycean world featuring hydrogen atmospheres and deep water layers. Each new dataset provides a clearer picture of how diverse the universe can truly be now. We look toward the stars, not with haste, but with a quiet desire to understand our origins. If you enjoy these deep explorations in space, consider subscribing or hitting the like button. It really helps the channel grow and allows me to make content like this. The stillness of the vacuum serves as a canvas for the light traveling across the great void. As we process these signals, we find ourselves drifting further into the mysteries of the cosmic sea. Every photon captured by the golden mirrors tells a story of a place we may never visit. The silence of the laboratory matches the silence of the distant stars as we wait for clarity. You are considering a point of light that resides in the constellation of Leo, a coordinate in the immense velvet of the night. This point is K-18b, a world 8 times the mass of our own, resting in the habitable zone of its star. To think of this place is to think of steady, low-energy light from a red dwarf washing over a horizon we cannot see. The data arrives not as an image, but as a series of dips in a graph, a rhythmic pulse of information. You might find comfort in the stability of these measurements, the way the light remains consistent over vast periods. The James Webb Space Telescope sits in the cold isolation of the second Lagrange point, far from the heat of Earth. It watches. It waits for the moment the planet crosses the face of its star, a transit that reveals the invisible. As the starlight filters through the planet's air, certain colors are absorbed by the molecules present there. Carbon dioxide leaves a shadow, methane leaves a fingerprint. These are the quiet echoes of a world that is fundamentally different yet strangely familiar in its chemistry. We are beginning to see the outlines of a place where the air is thick and the shadows are long. There is no rush to reach a conclusion, only the slow unfolding of evidence. You are safe here, observing the results of a billion-mile journey taken by a single beam of light. The light you are perceiving now began its departure from the K-18 system over a century ago, traveling through the absolute stillness of the interstellar medium to find its way to our mirrors. This photon-driven narrative is one of extreme patience, where the silence of the telescope mirrors the silence of the space it surveys. As we lean into the data, we find that the planet K-18b is not merely a point of light, but a physical reality with a weight, a temperature, and a presence that subtly alters the starlight passing through its outer edges. Imagine the atmosphere as a delicate filter, a thin veil of gases that acts as a prismatic messenger. When the planet moves between us and its host star, the light must navigate this gaseous terrain. Each molecule of methane, each pocket of carbon dioxide, and each trace of water vapor acts as a tiny obstacle, absorbing specific frequencies and letting others pass through. This process, known as transmission spectroscopy, is the primary tool of the scientist observer. It is a method of deduction that relies on what is missing rather than what is seen. We are looking for the shadows cast by atoms. By measuring the light that doesn't arrive, we reconstruct the composition of a world that remains visually unreachable. This is the art of scientific inference, a quiet and meticulous reconstruction of a distant reality. The environment of K-18b is classified as a Hycean world, a portmanteau of hydrogen and ocean. These worlds represent a category of exoplanet that we do not have in our own solar system. While Earth is a rocky world with a relatively thin atmosphere, and Neptune is a gas giant with no solid surface, a Hycean world exists in the curious middle ground. It possesses a massive hydrogen-rich atmosphere that exerts immense pressure on a global ocean below. To stand conceptually on such a world would be to experience an environment where the sky and the sea are intrinsically linked in a heavy, humid embrace. The pressure at the interface of the water and the air would be so significant that the properties of the water itself might shift into states we only see in laboratory settings. There is a profound sense of continuity in the way these planets form. In the early stages of a star system, the distribution of materials is governed by the heat of the central sun. Further out, beyond the snow line, water and gases are more abundant, allowing planets to grow larger and retain thicker envelopes of hydrogen. K-18b sits at a point of balance, close enough to its red dwarf to keep its water in liquid form, yet massive enough to hold onto its primordial gases. This balance is a slow, evolutionary achievement of the cosmos. It is the result of gravity and thermodynamics working together over billions of years to create a stable, enduring world. As we drift further into this section, we see that the stability of this system is its most comforting feature. The red dwarf star, K-18, is a constant companion, providing a steady but dim radiance. Unlike our yellow sun, which burns bright and hot, a red dwarf is cooler and more focused in the infrared spectrum. This means that the light reaching the planet is softer, casting a deep, amber glow across the cloud tops. The shadows on K-18b would not be sharp or harsh, but long and diffused, blending into the heavy atmosphere. There is no sudden midday glare here. Instead, the world exists in a state of perpetual evening. This low-energy environment suggests a slow metabolism for the planet itself, a place where changes happen over centuries rather than days. The scale of time here is vast, matching the scale of the space that separates us. Within this thick atmosphere, the James Webb Space Telescope has identified the clear signatures of methane and carbon dioxide. On Earth, methane is often associated with biological processes, though it can also be produced through geological activity. Carbon dioxide is a fundamental component of planetary temperature regulation. Seeing them together in a hydrogen-rich atmosphere provides a glimpse into a complex chemical cycle. We observe the way these gases interact, noting the absence of ammonia, which suggests that a liquid ocean exists beneath the clouds, absorbing the nitrogen-based compounds. This is a quiet revelation, a piece of a puzzle that we are solving without ever leaving our own orbit. The evidence is unfolding at a pace that allows for deep reflection and calm consideration. To understand the scale of the ocean on K2-18b, one must think of a world where there are no continents to break the horizon. The water would be an endless expanse, a global sea that wraps around the entire planetary sphere. The waves would be driven by the gravitational pull of the red dwarf and the internal heat leaking from the planet's core. Because the planet is so much more massive than Earth, the waves might move with a heavy, rhythmic deliberation, their crests long and their troughs deep. The sound of such an ocean, if there were ears to hear it, would be a low, constant thrumming, a deep frequency vibration that echoes through the water. It is a world of fluid motion, a place where everything is in a state of slow, graceful flux. The atmosphere above this ocean is not just a collection of gases, it is a dynamic system of weather and light. The hydrogen-rich air would be much lighter than our own nitrogen-oxygen mix, but the sheer volume of it would make it feel dense and substantial. Clouds of water vapor might form at various altitudes, drifting in slow currents across the globe. These clouds would act as mirrors, reflecting the dim red light of the star back into space, or trapping the heat from the ocean below. The thermal equilibrium of such a world is a delicate dance between the incoming stellar energy and the insulating properties of the hydrogen. It is a system that has found a quiet, steady state, a balance that has persisted for eons. As we continue our observation, we move into the realm of uncertainty with a sense of calm acceptance. One of the most intriguing findings is the potential presence of dimethyl sulfide. This molecule is particularly interesting because, on our own world, it is produced primarily by phytoplankton in the oceans. In the context of K2-18b, its presence is a faint whisper, a signal that is currently at the very limit of our detection capabilities. We do not claim it is a sign of life, but we recognize it as a possibility that requires further study. This uncertainty is not a cause for excitement or alarm, but a reason for continued, patient observation. The universe is revealing its secrets slowly, one molecule at a time. There is a sense of peace in knowing that there are places in the universe that are so fundamentally different from our own, yet governed by the same underlying principles of physics and chemistry. The atoms of carbon on K2-18b are identical to the atoms of carbon in the trees outside your window. The water molecules in that distant ocean are built of the same hydrogen and oxygen that make up the rain. This chemical kinship is a bridge across the void, a reminder that we are part of a unified cosmic system. The vastness of the distance is bridged by the consistency of the laws of nature. We can look at a world 120 light-years away and understand its composition because the universe is coherent. The process of data collection is itself a meditative act. The telescope must point with incredible precision, holding its gaze on a single star for hours or days at a time. The mirrors, cooled to temperatures that would freeze the very air we breathe, must remain perfectly still. This mechanical patience is a reflection of our own desire to understand the stars. We build these instruments to extend our reach, to see the invisible, and to listen to the silent echoes of the deep past. Every bit of data that arrives is a gift of time and technology, a small light in the darkness of our ignorance. We process this information with a quiet humility, aware of how much we have yet to learn. The transit of K2-18b is a rhythmic event occurring every 33 days. This regularity provides a sense of comfort, a heartbeat in the cosmic dark. Each transit is a new opportunity to refine our measurements, to check our previous findings, and to look for new details. We are not in a race to find the answers. We are engaged in a long-term conversation with the universe. The planet passes, the light dims, the data flows, and we wait for the next cycle. This repetition is a fundamental part of the scientific process, a slow accumulation of knowledge that builds over years and decades. It is a journey of 1,000 steps, each one taken with care and deliberation. In the thick air of K2-18b, the concepts of day and night might be very different from our own. If the planet is tidally locked, a common occurrence for worlds orbiting so close to red dwarfs, one side would always face the star, while the other would be in eternal darkness. This would create a world of extremes, but also a world of constant, stable transition zones. In the Terminator region, where the sun is always on the horizon, the light would be a permanent sunset. Here, the temperature might be most balanced, and the winds would flow in a continuous cycle from the hot side to the cold side. This is a place of perpetual twilight, a quiet and atmospheric realm where the clouds are illuminated from below by the glow of the ocean and from above by the red sun. The perspective we gain from studying K2-18b is one of profound insignificance, but also of deep connection. We are small, yes, but we are the observers. We are the ones who can decode the light and see the oceans on a world we can never visit. This ability to understand the distant is a testament to the power of the human mind and the persistence of our curiosity. We are drifting through a universe that is vast and mysterious, but it is also a universe that is knowable. The more we learn about worlds like K2-18b, the more we understand the context of our own home. We are one planet among billions, a small part of a larger story that is still being written. As the data settles into our models, we find that the mystery of K2-18b is not something to be solved and discarded, but something to be inhabited. The uncertainty of the dimethyl sulfide, the depth of the ocean, the exact composition of the clouds, these are questions that stay with us, providing a sense of ongoing wonder. We do not need the answers to be immediate. The mystery itself is a form of engagement, a way of staying connected to the larger cosmos. We are comfortable in the unknown, knowing that every observation brings us one step closer to the truth, however slow that progress may be. The light from K2-18b continues to arrive, a steady stream of photons that has survived a century-long journey through the void. Each one is a messenger, carrying a tiny piece of information about a distant sea. We receive these messengers with the same stillness with which they traveled. There is no urgency in our analysis, only a quiet, sustained interest. The world we are seeing is a place of deep water and red light, a place of heavy air and long shadows. It is a world that exists in its own time, following its own path, indifferent to our gaze. We are merely the witnesses, the quiet narrators of a story that spans the galaxy. In this state of observation, the boundaries between the telescope, the scientist, and the planet begin to blur. We are all part of the same physical reality, moving through the same space-time. The atoms that make up the mirrors of the telescope were once part of a star, just as the atoms in the atmosphere of K2-18b were. The continuity of matter and energy is the ultimate truth of the cosmos. As we watch the planet transit its star, we are watching a fundamental process of the universe, the interaction of light and matter. This is the foundation of everything we know. The drift continues, moving from the specific chemistry of a distant world to the broader realization of our place in the stars. We are safe in this knowledge, grounded by the facts and inspired by the mysteries. The universe is a vast, quiet place, filled with worlds that are waiting to be understood. K, 2-18, B is just one of them, a single coordinate in the velvet dark. We will continue to watch, to listen, and to learn, moving with the same slow and steady pace as the light that brings us the news of the stars. The evidence will continue to unfold, the shadows will continue to lengthen, and we will remain here, observing the results of a billion-mile journey, one photon at a time. What makes this strange is not just the heat, but the stillness. On the surface of Venus, the wind moves slowly, but the air is so heavy it would feel like walking through waist-deep water. It is a world where time seems to have thickened. It takes longer for Venus to rotate once on its axis than it does for it to orbit the Sunday. A day on Venus is longer than a year on Venus. It is a place where the usual rules of time and light are reversed. And then we reach Earth. We often forget that we are part of this inner circle. We see the Earth as a world unto itself, but in the context of the solar system, we are simply the third rock from the Sunday. We are located in what scientists call the Goldilocks zone, the region where it is not too hot and not too cold for liquid water to exist. This is our human-scale anchor. Everything we understand about geology and biology starts here, on this wet, blue sphere. Beyond Earth lies Mars, the final member of the inner circle. Mars is a world of ancient mysteries. It is half the size of Earth, a cold, dry desert that was once, perhaps, a world of rivers and lakes. When we look at the surface of Mars, we see the echoes of a lost era. We see the largest volcano in the solar system, Olympus Mons, which stands 3 times higher than Mount Everest. We see Valles Marineris, a canyon so long it would stretch across the entire United States. Scientists understand Mars by sending robotic explorers to taste its dust and listen to its wind. What we know so far suggests that Mars lost its internal heat and its magnetic shield long ago, allowing the solar wind to slowly strip away its atmosphere. It is a world in a state of deep freeze, a preservation of a time when the inner solar system was a more violent and active place. But even with everything we've learned, there are still things we don't fully understand. We see the seasonal changes in the Martian polar caps, the shifting sands, and the strange traces of methane in the air. We don't know if life ever took hold there, or if it still clings to existence beneath the surface. Not because we're missing something urgent, but because the universe moves slowly, and the evidence of ancient life is buried under billions of years of red dust. And for now, that uncertainty is simply part of the picture. It doesn't need to be resolved tonight. We can accept the red planet as a silent neighbor, a place of potential and of history. As we look at these 4 worlds together, we see a pattern of density and proximity. They are the inner circle because they are the only ones capable of surviving so close to the sun's fire. They are the anchors of our reality. They are the rocky foundation upon which the rest of the solar system is built. Think about the space between these worlds. Even in the crowded inner circle, the distances are immense. If you were standing on Mars, looking back at Earth, our home would look like a bright blue star, indistinguishable from the other lights in the sky to the untrained eye. The void is already beginning to assert itself. The sun, while still the dominant force, is beginning to look smaller as we prepare to cross the Great Divide. The inner circle is a place of activity of volcanoes, of atmospheres, of shifting plates and crashing asteroids. But as we move outward, this activity begins to cool. The energy of the sun begins to stretch thin. We are entering a phase of the journey where the stuff of the universe becomes less solid and more ethereal. You can feel the transition in the rhythm of your own thoughts. The concrete world of rock and metal is behind us. The familiar landscapes of craters and canyons are fading. We are moving toward a region where gravity is the only thing that remains constant. The inner planets have provided us with a safe, solid beginning, but the true scale of the solar system is found in the gaps that lie ahead. With that in mind, let's move outward once more, to an even larger scale, beyond the reach of the rocky worlds, toward the great debris field that separates the inner system from the giants, toward the silence of the belt and the immense gas-shrouded worlds that wait in the cold. We are leaving the hearth. We are moving into the halls of the kings. This transition is not merely a change in distance, but a change in the very texture of reality. We are crossing a threshold where the sun's warmth becomes a memory, and the density of matter begins to dissolve into the ethereal. As we drift away from the red dust of Mars, the landscape of our solar system undergoes a radical transformation. Behind us, the 4 terrestrial planets are huddled like embers in a fireplace. Ahead of us lies the asteroid belt, a vast, ring-shaped region that serves as the cosmic border between the inner and outer systems. People often imagine this belt as a chaotic obstacle course of tumbling boulders, but to understand its true scale, we must return to our state of patient observation. Imagine the distance between Mars and Jupiter. It is a gap wider than the entire distance from the Sun to Mars. In this immense no man's land, there are millions of fragments of rock and ice, ranging from the size of a dust mote to the size of a dwarf planet like Ceres. But despite there being millions of these objects, the space they inhabit is so vast that the belt is almost entirely empty. If you were standing on a typical asteroid, the next nearest one would be an average of 600,000 miles away. That is more than twice the distance from the Earth to the Moon. You would be standing in a profound, uninterrupted solitude, looking out at a sky where your nearest neighbor is just a tiny, unmoving pinprick of light. Scientists understand the asteroid belt not as a failed planet, but as a collection of building blocks that were never allowed to come together. The immense gravitational influence of Jupiter, the giant that looms just beyond the belt, acted like a cosmic spoon, stirring the debris and preventing it from coalescing into a single world. This challenges how we think about missing pieces of the universe. Sometimes, the universe doesn't complete its projects. Sometimes, it leaves the raw materials scattered across the dark, a permanent museum of what might have been. What makes this strange is the sheer variety found within this silence. We see Ceres, a spherical world of rock and ice that contains a quarter of the belt's total mass. we see Vesta, a dry, basaltic remnant of a protoplanet. We see metallic asteroids that are essentially floating mountains of iron and nickel. Astronomers didn't expect to find such a diverse chemical library in what was once thought to be a uniform field of rubble. It suggests that the early solar system was a place of violent mixing and migrating orbits, a chaotic birth that eventually settled into the quiet continuity we see today. As we move through the belt, the light of the sun begins to change. It is no longer the golden, life-giving glow of an afternoon on Earth. It is becoming cooler, whiter, and more distant. We are crossing the frost line, the invisible boundary beyond which volatile compounds like water, ammonia, and methane can condense into solid ice. Inside this line, the sun's heat kept these materials in a gaseous state, blowing them toward the outer reaches. Outside this line, the universe begins to build with ice. This transition is the reason for the Great Divide in planetary size. Once we pass the frost line, the stuff available to build planets changes from scarce rock to abundant ice and gas. It is as if we have moved from a small village built of stone to a sprawling metropolis built of clouds. The scale of what lies ahead is so much larger than what we have left behind that it requires a second mental reset. The inner planets are merely the preamble. The gas giants are the main body of the work. Over immense periods of time, these outer worlds have gathered up the lion's share of the solar system's heritage. To understand this, we must look at the way gravity behaves at this distance. In the inner system, gravity is a sharp, local force. Out here, it is a broad, sweeping power. We are approaching Jupiter, a world so massive that it doesn't just have moons. It has a family of 79 confirmed satellites, a miniature solar system in its own right. But even as we approach these giants, the most striking feature remains the distance. Between the outer edge of the asteroid belt and the beginning of Jupiter's atmosphere, there is a gap of nearly 300 million miles. Think back to our grain of salt, 15 yards from the grapefruit. By the time we reach the inner edge of Jupiter's territory, we have walked nearly 80 yards. The gaps are now larger than the entire inner solar system combined. This brings us to a state of cosmic acceptance. We realize that the order of the solar system is not one of crowded proximity, but of vast, measured isolation. Each world is a lonely sovereign, ruling over a territory of darkness that is millions of miles deep. The halls of the kings are not narrow corridors, but cavernous, silent spaces where the light of the sun is a precious, diminishing resource. Scientists understand the gas giants by listening to the radio waves they emit, deep, haunting groans caused by their massive magnetic fields interacting with the solar wind. What we know so far suggests that these worlds are essentially unfinished stars. If Jupiter had been 80 times more massive, it might have ignited, giving our system a second sun. Instead, it remains a cold, swirling masterpiece of fluid dynamics, a world where the weather lasts for centuries and the surface is a transition from gas to liquid that has no clear boundary. And for now, that ambiguity is simply part of the picture. We don't need a solid ground to stand on to appreciate the scale. We can drift in the upper layers of these atmospheres, feeling the immense pressure of the scale above us and the vast emptiness of the scale around us. The inner circle was about the solid and the certain. The outer system is about the immense and the fluid. As you allow your mind to settle into this deeper, colder region, notice how the rhythm of the journey has slowed. The inner planets moved fast, their years measured in months. Out here, the pace is more deliberate. Saturn takes nearly 30 years to complete a single circuit. Uranus takes 84. Neptune takes over 160. We have entered the realm of long time, where the movements of the heavens are measured in human generations. There is a gentle humility in this realization. We are travelers in a system that does not operate on our schedule. The solar system is a clock that ticks in centuries, not seconds. As we move further into the halls of the kings, let the weight of your own timeline lift. You are stepping into a continuity that is ancient, silent, and incredibly vast. The rocky world you left behind is now just a bright spark in the distance, a grain of salt lost in a quarter-mile field. With that in mind, let's move outward once more, to an even larger scale. Beyond the giants, toward the blue shadows of the ice worlds and the final frozen fragments of the sun's reach, we are leaving the gas shroud behind. We are moving toward the true edge of the light. Now, let's slowly expand outward. Beyond the orbit of Mars, the character of our solar system begins to change. We enter the asteroid belt. In movies, this is often shown as a crowded field of tumbling rocks, where a pilot must dodge and weave to survive. But the reality is much more peaceful and much emptier. To understand this region, we have to let go of the idea of stuff and embrace the idea of room. The asteroid belt is the first great transition zone of our system, a vast, silent clearing that separates the warm, rocky inner planets from the cold, gaseous giants that loom further out in the dark. If you were standing on an asteroid in the middle of the belt, you likely wouldn't see another asteroid with your naked eye. They are millions of miles apart. The belt is not a wall of stone. It is a vast, sparse desert where the occasional mountain-sized rock drifts in a slow, lonely circle around the sunday. There are millions of these objects, yet they represent less than 1% of the mass of our moon. This is the Great Divide, and it serves as a reminder that the solar system is not a crowded place. It is a series of lonely islands separated by oceans of nothingness. Imagine you are on a journey across this divide. You have left the red, dusty horizon of Mars behind. As you move forward, the sun begins to shrink. It is no longer a dominant, heat-giving disk. It is becoming a brilliant, piercing light, shedding its warmth but keeping its hold on you. In this region, between the orbit of Mars and the orbit of Jupiter, we find the rubble of the solar system. These are the fragments of a story that never quite finished. Scientists understand the asteroid belt not as the remnants of a destroyed planet, but as the raw materials of a planet that was never allowed to form. The gravity of Jupiter, which we will encounter soon, is so immense that it acted like a cosmic stirrer, keeping these rocks moving too fast to ever clump together. What we know so far suggests that if you were to gather every single asteroid in the belt, every grain of dust, and every mountain of iron, and smash them together into one sphere, it would be smaller than our own moon. It is a vast territory with very little to show for it in terms of mass. But what the belt lacks in mass, it makes up for in mystery. We see objects like Ceres, a dwarf planet that accounts for a third of the entire belt's weight. Ceres is a world of its own, with a crust of ice and perhaps a hidden ocean beneath its surface. Astronomers didn't expect to find a world so complex in the middle of a debris field. It challenges how we think about active worlds. Even here, in the cold divide, there are processes at work that we are only beginning to comprehend. What makes this strange is not what we find, but how quiet it all is. We are used to a world where nature means trees, wind, and movement. But in the Great Divide, nature is the absence of these things. It is the slow, silent drift of a billion-year-old rock. It is the way a shadow falls across a crater that hasn't changed since the dawn of the dinosaurs. This is a place of deep time. Think back to our human-scale anchor. If the distance from the Sun to the Earth was the length of a single room, the asteroid belt would be the hallway leading to the rest of the house. It is a transition. It is the space you pass through to get somewhere else. But while you are in the hallway, you can feel the shift in atmosphere. The air, if there were air, would feel thinner. The light would feel sharper. You are leaving the living room of the inner system and moving into the grand, cold galleries of the outer giants. Astronomers often look at the asteroid belt as a time capsule. Because there is no wind or water to erode these rocks, they are exactly as they were 4 billion years ago. They are the fossils of the solar system's birth. When we study them, we are looking at the original building blocks of the Earth. We are looking at our own history, frozen in the vacuum. And for now, that stillness is simply part of the picture. It doesn't need to be filled with action. You can imagine yourself drifting through this belt, passing a mountain of iron that glows faintly in the distant sunlight. You don't need to dodge. You don't need to worry. There is enough room here for everyone. The gaps between the rocks are so wide that you could fly 1,000 spaceships through the belt in a straight line and never hit a single thing. This brings us to a state of calm insignificance. We realize that even the boundaries of our solar system are mostly made of peace. The Great Divide is not a barrier, it is a buffer. It protects the inner worlds from the chaos of the outer system, and it provides a quiet space for the mind to expand. To understand the scale of the divide, we must look at the time it takes to cross it. A probe traveling from Mars to Jupiter takes years to make the trip. For years it sees nothing but the distant stars and the shrinking Sunday. It is a journey through a void that seems to have no end. But eventually, the influence of the inner system fades completely, and a new power begins to take hold. We are approaching the edge of the divide. The rocky fragments are becoming fewer and farther between. When we think about the solar system, we often imagine it in human terms. Distances we can walk, time we can measure in years, objects we can see with our own eyes. We look at a map of the planets, and our brains instinctively try to shrink the cosmos down into something manageable, something that fits on a kitchen table or a classroom poster. But the reality is that the solar system is not a collection of objects. It is a collection of distances. It is an exercise in emptiness, punctuated only occasionally by the smallest specks of matter. To understand where we are, we have to first understand how much where there actually is. Imagine, for a moment, that you are going for a walk. You know the weight of your footsteps on the pavement. You know how long it takes to walk to the end of your street or to the local park. If you walked at a steady, brisk pace for an entire hour, you would cover about 3 miles. In our daily lives, 3 miles is a substantial distance. It is enough to change the scenery, to move from a busy downtown to a quiet suburb. But in the context of the solar system, that hour of walking hasn't even moved you the width of a single hair on the scale of the worlds we are about to discuss. To truly grasp the human-scale perspective, we must use an analogy that strips away the confusing billions of miles and replaces them with things you can visualize. Let us use the grapefruit analogy again, but let's walk through it slowly, feeling every step of the journey. Imagine you are standing in the center of a vast, empty salt, flat, level ground, stretching to the horizon in every direction, silent and still. In your hand, you hold a grapefruit. This grapefruit represents the Sunday. It is warm, it is bright, and it represents 99.8% of all the matter in our entire solar system. Everything else, the planets, the moons, the asteroids, and you, make up that tiny remaining 0.2%. Now, place that grapefruit on a small pedestal in the center of the salt flat. To find the Earth, you have to start walking. You aren't just stepping back a few feet. You walk past the first planet, Mercury, which is a tiny pinhead just 5 yards away from the grapefruit. You keep walking another 5 yards to find Venus, another pinhead. Finally, you reach a distance of about 15 yards, roughly the length of a large school bus, and you stop. There, on the ground, you place a single grain of salt. This is Earth. This grain of salt is your home. Everything you have ever known, every person you have ever loved, every war ever fought, and every dream ever dreamt has occurred on that tiny, crystalline speck sitting 15 yards away from a grapefruit. The first thing that strikes you in this silence is the space. Look back at the grapefruit. From the perspective of your grain of salt, the grapefruit looks small. It's about the size that the actual sun appears in our sky. But look at the ground between you and the grapefruit. There is nothing there. No cosmic dust clouds, no crowded asteroid fields. Just 15 yards of empty air. If you were an ant standing on that grain of salt, the distance to the grapefruit would seem like an infinite journey. Now, let us continue our walk. We want to find the outer reaches of the neighborhood. To reach Mars, the red pinhead, you walk another 7 yards. You are now 22 yards away from the Sunday. The distance is growing, and the grapefruit is looking smaller now. But we are still in the inner circle. To find the next planet, Jupiter, you have to be prepared for a hike. You leave the inner planets behind and start walking across the salt flat. You walk past the 30-yard mark, the 40-yard mark. You keep going until you are nearly 80 yards away from the grapefruit, almost the entire length of a football field. There, you find a cherry tomato. This is Jupiter, the king of the planets. Even though it is the largest planet, compared to the grapefruit, it is still just a small piece of fruit, and the distance between your grain of salt and this cherry tomato is 65 yards of absolute nothingness. As you stand by the cherry tomato and look back toward the center, the grapefruit is now a small dot in the distance. Your home, the grain of salt, is invisible to the naked eye. You are beginning to feel the true scale. But we aren't finished. To reach Saturn, you have to double your distance again. You walk until you are 140 yards away from the grapefruit. To reach Uranus, you walk to 280 yards. By the time you reach Neptune, the final major planet, you are nearly 450 yards away, more than a quarter of a mile from where you started. Stand there for a moment at the Neptune marker. You are a quarter mile away from a grapefruit. If you look back, you cannot see the grain of salt that is Earth. You can barely see the grapefruit. The solar system that we see on posters as a crowded family of planets is, in reality, a vast, lonely desert where the participants are so small and so far apart that they almost don't exist. This challenges how we think about our place in the world. We feel big, we feel important, but on the scale of the grapefruit and the salt flat, we are essentially a ghost. The silence of this perspective is not meant to make you feel insignificant in a negative way. Rather, it is meant to provide a sense of profound relief. All of the pressures of your daily life, the deadlines, the worries about the future, they all exist on that grain of salt. And that grain of salt is safely tucked away in a corner of a quarter-mile wide field of peace. Scientists understand this scale, not just through distance, but through time. If you wanted to send a message from your grain of salt to the cherry tomato of Jupiter using light, the fastest thing in the universe, it would take about 40 minutes for the message to arrive. If you were Neptune and you wanted to call Earth, you would have to wait 4 hours for your hello to reach home and another 4 hours for the reply. The solar system is a place where even conversation happens in slow motion. What makes this strange is not the distances themselves, but the fact that gravity manages to hold it all together. That grapefruit, all the way back at the center, is pulling on the speck of dust that is Neptune nearly half a mile away, with enough strength to keep it in a perfect, steady circle. It is a delicate, invisible clockwork. As you imagine yourself standing on that salt flat, the sun beginning to set, the grapefruit glowing faintly in the distance, you can feel the air grow still. You are a human-scale observer in a cosmic-scale reality. You are small, yes, but you are the only thing in this quarter-mile radius that is capable of understanding the map. You are the mind that holds the grapefruit and the salt grain together. For now, that understanding is enough. You don't need to walk any further tonight. You can simply stand here, in the quiet of the salt flat, and realize that the scale of the universe is not a wall, but an invitation. It is an invitation to let go of the small things and embrace the vastness. With that in mind, let's move outward once more, to an even larger scale. This is where the human brain begins to feel the first gentle tug of the impossible. We have spent our lives navigating a world where a 5-mile hike is a morning's commitment and a cross-country flight is a significant journey. But as we step away from our grain of salt and our grapefruit, we have to abandon these units of measurement. They no longer serve us. They are like trying to measure the depth of the ocean with a thimble. To move forward, we must change our pace, transitioning from the physical act of walking to the mental act of drifting. Think about the speed of a commercial airliner cruising at 500 miles per hour. At that speed, you can cross an entire continent in an afternoon. It feels fast. You look out the window and see the clouds racing by, the landscape shifting beneath you. But if you were to fly that same plane from our grain of salt toward the sun, you wouldn't arrive for 21 years. You would spend 2 decades in the air, flying day and night, just to reach the nearest star. This realization is the first scale reset. It forces us to acknowledge that the empty space we often ignore is actually the most dominant feature of our environment. As we continue to expand our perspective, we encounter the first major boundary of our planetary neighborhood. In our everyday lives, we are used to boundaries that are clear: a fence, a shoreline, a city limit. In space, boundaries are more like gradients, where the influence of one thing slowly fades as the influence of another begins to take hold. We are moving toward a scale where the gaps between objects are so large that the objects themselves start to feel like accidental interruptions in a much larger story of stillness. Consider the Moon, our closest neighbor. In most diagrams, it sits just a few inches away from the Earth. But on our human scale, if the Earth were a basketball, the Moon would be a tennis ball located 30 feet away. Think of that empty 30-foot gap. You could fit every other planet in the solar system, Jupiter, Saturn, the ice giants, all of them, side by side, inside that single gap between the Earth and the Moon, and you would still have room to spare. This is the lunar gap, and it is our first true lesson in cosmic density. We live in a universe that is incredibly efficient at being empty. As we drift further, the numbers begin to lose their edges. We talk about millions of miles, but the human mind treats a million the same way it treats a billion as a lot. To stay grounded, we must return to the feeling of time. Imagine a clock that ticks only once every century. On the scale we are entering, that clock would seem to be moving quite fast. The solar system operates on a rhythm that ignores the frantic pace of human history. The mountains on our grain of salt rise and fall in the time it takes for the outer planets to make just a few laps around the Sunday. Scientists understand this slow-motion reality by looking at the human-scale anchors that still exist within it. We look at the light that reaches us from the Sunday. That light, traveling at 186,000 miles per second, takes 8 minutes to cross the 15 yards of our salt-flat model. When you step outside and feel the warmth of the sun on your skin, you are feeling energy that left its source 8 minutes ago. You are always living in the past, seeing the sun not as it is now, but as it was when you were perhaps just starting a conversation or finishing a cup of tea. This delay is a constant reminder that distance and time are woven together. What makes this strange is not that the universe is big, but that it is so sparsely populated. We are used to a world of constant stimulation noises, lights, people, traffic. But as we expand to the scale of the inner solar system, the stimulation drops to nearly zero. If you were floating in the space between Earth and Mars, there would be no sound, there would be no wind, there would be no sense of movement, even if you were traveling at thousands of miles per hour. Without a nearby object to provide context, speed becomes an abstract concept. You are simply there, suspended in a vast, dark cathedral of light. Astronomers didn't expect the vacuum to be quite so profound until they began sending probes across these distances. They found that space isn't just empty. It is a vacuum more perfect than anything we can create in a laboratory. It is a place of total preservation. A footprint on the Moon stays there for millions of years because there is no weather to wash it away. The scale of the solar system is also a scale of permanence. On Earth, we are used to things breaking, rusting, and fading. In the vastness between the worlds, things simply endure. And for now, that endurance is simply part of the picture. It provides a sense of stability. As you continue to drift in your mind, let the vastness of these gaps act as a blanket. There is so much room in the universe for everything to simply be. There is no crowding here. There is no rush. Every planet has its own vast territory, millions of miles of private space in which to perform its slow, ancient dance. We often feel the need to fill silence with words or empty spaces with objects. But the solar system teaches us the value of the void. The void is not a lack of something, it is a thing in itself. It is the stage upon which the planets play. It is the dark velvet that makes the stars shine. By embracing the human-scale perspective of this emptiness, we can begin to let go of our own need to constantly be doing. We can transition from being actors to being observers. To understand the scale of the outer system, we need to step back even further. If our quarter-mile salt flat represented the distance to Neptune, the distance to the next nearest star, Proxima Centauri, would be another 2,000 miles away. Imagine that. You have a grapefruit in one city, and the next grapefruit isn't in the next neighborhood or the next town. It's on the other side of the continent, and in between, nothing, just thousands of miles of empty salt flats, with the occasional grain of salt or cherry tomato drifting in the dark. This challenges how we think about the neighborhood of our Sunday. We aren't just in a large space, we are in a staggering isolation. But this isolation is what makes our small grain of salt so remarkable. In a continent of empty flats, a single grain of salt that holds life, water, and consciousness is a miracle of the highest order. The scale doesn't diminish us, it highlights us. It provides the contrast necessary to see how special the stuff of the universe really is. As we move toward the next phase of our journey, allow your breathing to slow down, matching the rhythm of the planets. You are no longer walking, you are no longer flying, you are simply expanding. The boundaries of your room have faded, the boundaries of your city have disappeared. You are now as large as the orbit of the Earth, circling the Sun in a slow, silent loop that takes an entire year to complete. There is no tension in this movement. It is the natural state of things. Everything in the solar system is falling, but it is falling in a way that perfectly balances its forward motion, creating the eternal circle of the orbit. It is a state of perpetual grace. You can feel that same balance in your own rest. You are supported. You are in motion, even when you are still. You are part of the clockwork. With that in mind, let's move outward once more, to an even larger scale, where the rocky worlds end and the giants begin. Where the light grows dim and the silence grows even deeper, we are leaving the inner circle, the warm hearth of the sun, and moving into the great, cool expanses of the outer dark. But do not worry. The scale will continue to guide us. The distances will continue to protect us, and the stillness will be our companion. Now let's slowly expand outward. One level beyond what we just explored lies the neighborhood of the inner planets: Mercury, Venus, Earth, and Mars. In the grand design of the cosmos, these are the rocky worlds. They are solid. They have surfaces you could, in theory, stand upon. They represent the high-density center of the sun's domain, a place where the gravity of our star is so intense that it has cleared away the lighter gases, leaving behind only the heavy elements, the iron, the silicate, and the nickel, to form these 4 small, resilient spheres. To understand the inner circle, we must first look at Mercury. It is the closest to the flame. If our sun is the center of a cosmic hearth, Mercury is the stone sitting directly in the embers. It is a world that has been stripped down to its essentials. It has no atmosphere to speak of, no clouds to shield it from the sun's relentless gaze. Because it lacks an atmosphere to trap heat, it experiences the most dramatic temperature swings in the solar system. By day, the surface is hot enough to melt lead. By night, it plunges into a frozen darkness more bitter than any winter on Earth. Scientists understand Mercury by observing the way it interacts with the Sun's magnetic field. It is essentially a giant ball of iron, a planetary core that seems to have lost its outer layers in some ancient, forgotten collision. It orbits the Sun with a strange, wobbling rhythm, completing 3 rotations for every 2 revolutions. It is a world that refuses to be tidally locked, yet it is forever bound to its master. To understand the cosmos, we first have to understand our own limitations. We evolved to perceive distances we can walk in a day, or see with our own eyes distances that matter for survival and navigation. A kilometer is a 10-minute walk. A mile is a 20-minute journey. These measurements are concrete and relatable because they fit into our daily lives. But the moment we look up, these human-scaled units become awkward and eventually useless. To explore the universe, we must leave behind the familiar and prepare for a scale that challenges our very ability to comprehend it. Our brains are essentially biological survival machines, fine-tuned over millions of years to solve problems on a local scale. When our ancestors stood on the African savanna, big meant the distance to the horizon or the height of a mountain. Fast was the speed of a sprinting predator or a falling stone. We developed a deep, intuitive relationship with the physical world, but it was a world restricted to a very narrow band of reality. This is our human-scale anchor. It is the comfort zone of the tangible. In this zone, we can estimate how long it takes to drive to the next city, or how many steps it takes to cross a room. We feel the weight of an object in our hands and know its mass. This grounding is necessary for life on Earth, but it acts as a mental barrier when we attempt to look beyond our atmosphere. Consider the humble meter or yard. These units are literally based on the human body, the length of a stride or the reach of an arm. When we use these units to measure a house or a street, they make perfect sense. Even when we scale up to the size of our planet, we can still, with effort, visualize it. We can imagine a flight across the ocean taking 12 hours, and our brains can loosely stitch together that duration with the physical distance covered. We can look at a globe and understand that the thin blue line of the atmosphere is fragile, but even at this stage, the anchor begins to drag. The Earth is roughly 12,742 kilometers in diameter. If you were to try to walk that distance without stopping, it would take you months of continuous movement. Already, the human scale is beginning to fray at the edges. The problem is that the universe does not operate on a human scale. It operates on a cosmic one. As soon as we leave the surface of our world, the numbers don't just get larger, they change in quality. They become abstract. When we say the moon is 384,400 kilometers away, the brain hears the number, but it cannot feel the distance. It loses the tactile connection it has with a kilometer-long walk. This is the lunar gap, the first true test of our ability to let go of our terrestrial anchors. To bridge this gap, we often use analogies, telling ourselves that you could fit 30 Earths in the space between us and the moon. We use these mental crutches because the raw data is too vast for our ancestral hardware to process. We are trying to run cosmic-scale software on hunter-gatherer hardware. This limitation isn't just a quirk of psychology, it's a fundamental challenge in how we communicate the story of space. If we cannot relate to the distance of our nearest neighbor, how can we hope to grasp the distance to the Sun? The Sun is 150 million kilometers away. At this point, the kilometer has become a redundant tool. Using it to measure the solar system is like trying to measure the width of the Atlantic Ocean using the thickness of a human hair. It is technically possible, but the resulting number is so large that it ceases to mean anything to the human mind. This is why we must transition into new units of thought. We have to learn to think in terms of light-time understanding that even at the fastest speed allowed by the universe, it still takes 8 minutes for a photon to travel from the sun to your eyes. By anchoring ourselves in the human experience first, we acknowledge our starting point. We admit that we are small, that our perspective is local, and that our intuition is often wrong when applied to the stars. This humility is the prerequisite for discovery. We must accept that our senses were never designed to perceive the curvature of space-time or the billion-year life cycles of stars. We are effectively scale blind. Just as a person born without the ability to see color must rely on instruments to tell them the sky is blue, we must rely on mathematics and technology to tell us the true dimensions of the void. The human anchor is also about time. We live for perhaps 80 or 90 years. To us, a decade is a significant portion of our existence. A century is ancient history. But in the cosmic script, a million years is a blink. The stars we see at night are not static. They are in violent, constant motion. But because their lives span billions of years, they appear frozen to our short-lived eyes. Our anchor in time is just as restrictive as our anchor in space. We view the universe as a still photograph, when in reality it is a chaotic, high-speed film. To understand space-themed stories, we have to mentally speed up our perception of time while slowing down our expectation of distance. Every story we tell about the stars is an attempt to pull the cosmos down to our level. When we talk about interstellar travelers or galactic empires, we are using human political and social structures to make the infinite feel intimate. We give names to constellations, warriors, queens, and animals to turn a terrifyingly vast vacuum into a familiar neighborhood. This is a necessary survival mechanism. Without the human anchor, the sheer scale of the universe would be paralyzing. It would be a total perspective vortex that could crush the human spirit under the weight of its own insignificance. But there is a beauty in this struggle. The fact that a creature whose world is measured in footsteps can calculate the mass of a black hole or the age of a distant galaxy is a testament to the power of the mind to transcend its biological limits. We are anchored to the Earth by gravity and to our history by evolution, but our curiosity is unanchored. We use the familiar, the walk, the mile, the minute, as a springboard to leap into the unfamiliar. We build mental ladders, starting with the human scale and slowly adding rungs of increasing magnitude until we can reach the stars. As we move forward into the deeper segments of the cosmic story, keep this anchor in mind. It is your point of reference. Every time we speak of a distance that breaks the brain, remember that it only breaks the brain because the brain was built for the forest and the field, not the vacuum. By recognizing the boundaries of our internal map, we can finally begin to explore the territory that lies beyond the edges. We are the bridge between the microscopic and the macroscopic. We are the observers who give the scale a name. In the following segments, we will leave the shore of the familiar. We will watch the Earth shrink until it is nothing more than a pale blue dot, and then we will watch that dot vanish entirely. We will see structures so large that they defy the cosmological principle, and we will encounter anomalies that suggest our current maps are incomplete. But no matter how far we travel, we always carry the human anchor with us. It is the "you are here" marker on the map of the infinite. It is what allows us to say, "I am small, but I am here, and I am looking." This realization that we are tiny observers in a vast theater is not a reason for despair, but a reason for wonder. The human anchor teaches us that scale is relative. To an ant, a backyard is a continent. To us, the Earth is a world. To the universe, we are a momentary flicker. But within that flicker, we have found the courage to look up and ask, how big is it all? And more importantly, where do we fit in? The journey starts here, with a single step, a 10-minute walk, and the realization that the horizon is much, much further than it looks. This realization that we are tiny observers in a vast theater is not a reason for despair, but a reason for wonder. The human anchor teaches us that scale is relative. To an ant, a backyard is a continent. To us, the Earth is a world. To the universe, we are a momentary flicker. But within that flicker, we have found the courage to look up and ask, how big is it all? And, more importantly, where do we fit in? The journey starts here, with a single step, a 10-minute walk, and the realization that the horizon is much, much further than it looks. To begin this expansion of our perspective, we must look at the tools we use to hold on to our reality. Think about your home. The average house is a space you can walk across in 30 seconds. You know the texture of the walls, the creak of the floorboards, and the exact distance from the front door to the kitchen. This is your primary anchor. It is a scale that makes perfect sense to your brain because you experience it every second of every day. Your brain evolved to understand these immediate, tactile spaces, areas you can see, touch, and navigate without a second thought. But when we move from the living room to the city, the anchor begins to slip. We start relying on technology, like cars and maps, to bridge the gap between what we can see and where we need to go. We are already abstracting our reality. The problem is that the leap from a city to a planet is nothing compared to the leap from a planet to the void. Imagine standing on a football field. It's about 360 feet long, a distance you could stroll across in 2 minutes. Now, imagine laying 17 of those fields end to end. That is a mile. Comet. A mile is a distance most of us can still visualize. It's a 20-minute walk, a common measurement for a morning jog. But to reach the edge of our own atmosphere, you would need to stack 62 miles of those football fields vertically. This is the Kármán line, the invisible boundary where the sky turns to space. Even at this relatively short distance, our human intuition fails. We cannot see 62 miles up. We only see a blue haze that fades into black. This brings us to the lunar gap. The moon is our closest neighbor, sitting approximately 238,855 miles away. To a human brain, that number is just a digit on a page. To bring it back to the anchor, consider this. If you could drive a car at highway speeds toward the moon, it would take you nearly 6 months of non-stop driving to get there. No red lights, no gas stations, just 160 days of driving through a vacuum. If you chose to walk, it would take you 9 years. This is the first rung on the cosmic ladder, where the human scale starts to feel absurd. We use these analogies like fitting 30 Earths between us and the moon, not because they are scientifically precise, but because they are the only way to prevent our minds from shutting down in the face of such emptiness. Once we pass the moon, the anchor is no longer dragging, it is severed. The distance to the sun is 93 million miles. This is the solar anchor, the unit we call an astronomical unit, AU. If the moon was a 9-year walk, the sun is a walk that would take you 3,500 years. You would need 40 generations of your descendants to keep walking just to reach the light. This is why we stop using miles and start using light time. Light is the fastest thing in the universe, traveling at 186,000 miles per second. It can circle the Earth 7 times in a single heartbeat. Yet, even at this impossible speed, it takes light 8 minutes and 20 seconds to reach us from the Sunday. When you look at a sunset, you are seeing the sun where it was nearly 9 minutes ago. You are already looking into the past. This temporal shift is a crucial part of the human anchor. We are used to things happening now. If you drop a glass, it breaks now. If you call a friend, they hear you now. But in space, now is a localized concept. The further out we look, the further back in time we see. This creates a strange paradox. The larger the universe gets, the older the information we receive becomes. By the time we look at the nearest star system, Proxima Centauri, we are looking 4 years into the past. If that star were to vanish today, we wouldn't know for another 4 years. We are anchored in a present that doesn't exist for the rest of the cosmos. To understand the scale of a galaxy like our Milky Way, we have to stretch the anchor until it breaks. Our galaxy is 100,000 light-years across. If you were to scale the entire Earth down to the size of a single grain of sand, the Milky Way would still be the size of the entire United States. Think about that for a moment. Every mountain, every ocean, every city, and every person who has ever lived, all shrunk into one speck of sand, and the neighborhood it lives in is still a continent wide. This is the true scale that makes Earth disappear. We aren't just small, we are mathematically insignificant in terms of volume. And yet the Milky Way is just a mid-sized galaxy. When we look at giants like IC 1101, which is 6 million light-years across, the Milky Way itself becomes the grain of sand. IC 1101 is so large it could swallow thousands of Milky Ways. It is a cosmic monster, a graveyard of galaxies that have been consumed over billions of years. At this scale, the human anchor is so far behind us that it's almost impossible to find. We are talking about structures that take millions of years just for a single particle of light to cross. If you were on one side of IC 1101 and sent a hello message to the other side, by the time it arrived, your entire species might have evolved into something else or vanished entirely. But why does this matter to us, the observers? It matters because it defines the cosmological principle, the idea that on a large enough scale, the universe looks the same everywhere. But Our recent discoveries of defiant anomalies suggest this might not be true. We have found structures like the Hercules Corona Borealis Great Wall, a filament of galaxies spanning 10 billion light-years. This structure is so large it shouldn't exist according to our current models of how the universe grew. It is a knot in the fabric of space that defies the smoothness we expected. These are the things that keep astronomers awake. They are the moments where our mathematical anchors fail, and we realize that the universe is even stranger than we imagined. We also encounter interstellar visitors like 3I, Atlas, or Oumuamua objects that don't belong to our sun. They come from the dark, silent reaches between stars, carrying secrets of other worlds. When we see these objects, the human anchor feels a different kind of tug. It's not just about size, it's about loneliness. We look at these drifting rocks and wonder if they were once part of a system like ours, or if they are the cold spots of a distant, dying sun. They remind us that our solar system is not a walled garden, but a porch light in a very dark forest. The human anchor is also a shield against the vast empty. Between the galaxies lie the voids, spaces, millions of light years across where there is almost nothing. No stars, no planets, just a few stray atoms per cubic meter. If you were placed in the center of the Boötes void, you wouldn't see a single star in the night sky. It would be total, absolute darkness in every direction. For a creature evolved to follow the sun and the moon, this kind of emptiness is a sensory nightmare. Our anchor helps us populate that darkness with meaning. We look at the Great Attractor, a mysterious gravitational anomaly pulling our entire region of space toward it, and we give it a name. We turn a terrifying physical force into a character in our cosmic story. Consider the smallness of our achievements. We have sent probes like Voyager 1 into the interstellar medium. It has been traveling for nearly 50 years at 38,000 miles per hour. In human terms, that is incredibly fast. In cosmic terms, it hasn't even left the front yard. It will take Voyager 40,000 years to reach the vicinity of another star. This is the reality of the distance that breaks our brains. We are a species that lives for decades, trying to conquer a universe that operates in eons. However, there is a flip side to this insignificance. If the universe is so large and we are so small, then the fact that we can understand it at all is a small miracle. We are an arrangement of atoms, carbon, nitrogen, oxygen forged in the hearts of dying stars. We are literally stardust that has come together in such a complex way that it can now turn around and study the stars that made it. The universe is looking at itself through our eyes. When we calculate the distance to a quasar or the mass of a supermassive black hole, we are the universe's way of knowing itself. The human anchor isn't just a limitation, it's a perspective. Without the anchor, size has no meaning. A galaxy is only big because we know what small feels like. The vacuum is only empty because we know what a crowded city street feels like. We provide the contrast. We are the yardstick by which the infinite is measured. Every space-themed story, whether it's about a journey to Mars or the collision of two galaxy clusters, is ultimately a story about us. It's about how our human hearts react to the cold, beautiful indifference of the stars. As we continue to explore, We must be prepared for our anchors to be tested again and again. We will find impossible stars that are older than the universe itself. We will hear strange signals from the deep that might be natural or might be something else. We will see giant circles in the sky that hint at events from before the Big Bang. Each time, we will try to drag our human-scale units, our kilometers and our miles out into the deep to make sense of it. And each time, they will fail us, forcing us to grow, to adapt, and to build a bigger anchor. The human anchor is our starting point, but it is not our destination. It is the solid ground we stand on before we take the leap. We must respect our limitations, but we must never be imprisoned by them. We are the bridge builders. We bridge the gap between the grain of sand and the galaxy. We bridge the gap between the 10-minute walk and the billion-year journey. So, as we move into the next segments of this general script, as we look at the true scale, the light years, and the anomalies, remember the anchor. Remember the smell of rain on pavement, the warmth of the sun on your skin, and the simple reality of a 1-mile walk. Hold those things close. They are what make the vastness of space worth exploring. They are the reason we look up in the first place. We don't go into the dark to get lost. We go into the dark to find out just how bright our own small light truly is. We have grounded ourselves. We have acknowledged our size. Now, we are ready to leave the shore. The horizon is calling, and though it is further than it looks, we have everything we need to begin the crossing. The universe is vast, but it is also ours to observe. And that, in the end, is the most human anchor of all. Imagine climbing a ladder where every new rung makes the previous one look microscopic. We begin with Earth, a world that seems enormous when you are standing on its surface, with oceans covering 71% of its face and mountains rising miles into the sky. But as we zoom out, Earth begins to shrink, not physically, but in significance. It stops being everything and becomes just one thing among many. Compared to the solar system, Earth is a speck. Compared to the galaxy, the solar system is a speck. And compared to the largest structures in the cosmos, even entire galaxies are like dust. To understand this ladder, we must first appreciate the rung we are currently standing on. To an early human, the Earth wasn't a planet. It was the floor of the universe. If you were to stand in the middle of a vast, flat plain, the horizon is only about 5 kilometers away. That was the limit of your world. Beyond that was mystery. Even today, with all our technology, the sheer physical bulk of the Earth is staggering. If you were to take a commercial flight from New York to Singapore, you would spend nearly 19 hours in the air, traveling at 500 miles per hour, and you would still only have covered a fraction of the planet's circumference. We perceive the Earth as a giant because, relative to our bodies, it is. We are 6-foot creatures living on a 12,000-kilometer sphere. But now, we take the first step up the ladder. We move from the Earth to its neighborhood, the inner solar system. As we pull away, the massive continents and vast oceans we just described begin to blur. At a distance of about 1 million kilometers, the Earth no longer looks like a world. It looks like a marble, and right next to it, relatively speaking, is the Moon. We often see diagrams of the Earth and Moon close together, but the reality is much emptier. You could fit every other planet in our solar system, Jupiter, Saturn, Mars, Venus, all of them into the space between the Earth and the Moon, and you'd still have room to spare. This is our first lesson in cosmic scale. Space is mostly empty. Even the crowded parts are defined by the gaps, not the objects. As we continue to climb, we reach the rung of the gas giants. This is where Earth's ego takes its first major blow. Jupiter is so large that 1,300 Earths could fit inside it. If Earth were the size of a grape, Jupiter would be the size of a basketball. Saturn, with its magnificent rings, isn't much smaller. These are worlds made of gas and liquid, with pressures so intense they turn hydrogen into metal. When you look at Jupiter's great red spot, a storm that has been raging for centuries, you are looking at a vortex that is wider than our entire planet. On this rung of the ladder, Earth has transitioned from the world to a minor rocky outpost. But the ladder doesn't stop at the planets. The next rung belongs to the Sunday. Our star is a yellow dwarf, a relatively average star, yet it contains 99.8% of all the mass in the solar system. You could fit 1 million Earths inside the Sunday. If the Sun were the size of a front door, the Earth would be the size of a nickel. At this stage, the scale of the planets, even Jupiter, starts to look trivial. The Sun's gravity is the anchor that holds everything together, reaching out billions of miles to the frozen edges of the Kuiper Belt. Yet, even the Sun is just a starting point. We climb higher, and now we are looking at the interstellar neighborhood. We are no longer measuring in miles or kilometers. We are measuring in the distance light travels in a year. The Sun, which seemed so dominant, begins to shrink into a tiny point of light. It joins a crowd of other stars, Alpha Centauri, Sirius, Vega. We begin to realize that our Sun is just one of 200 to 400 billion stars in the Milky Way. On this rung, the entire solar system, everything from the Sun to the furthest comet in the Oort cloud, is smaller than a single pixel on a high-definition screen. We have reached a level where the individual planets are literally too small to see. Now we reach the rung of the galaxy. The Milky Way is a barred spiral, a vast disk of stars, gas, and dust spinning through the void. It is 100,000 light-years across. To get a sense of this scale, if our entire solar system out to Neptune was the size of a white blood cell, the Milky Way would be the size of the continental United States. We are tucked away in one of the spiral arms, about 26,000 light-years from the center. At the heart of this massive structure is Sagittarius A*, a supermassive black hole 4 million times the mass of the Sunday. On this rung, the world we started with is not just a speck, it is an invisible ghost, an infinitesimal part of a much larger organism. But the ladder keeps going. We move to the local group. This is a collection of about 50 galaxies, including our own and our larger neighbor, Andromeda. These galaxies are bound together by gravity, dancing around each other in a dark cosmic ballet. The distance between the Milky Way and Andromeda is 2.5 million light-years. On this rung, even the 100,000 light-year span of our galaxy starts to look manageable. We are seeing galaxies not as vast expanses of stars, but as individual units, islands of light in a sea of nothingness. We climb further, reaching the rung of galaxy clusters and superclusters. We encounter the Virgo supercluster, which contains thousands of galaxies. And then we see the Laniakea supercluster, a structure so vast it defines our place in the local universe. Laniakea, which means immeasurable heaven in Hawaiian, is 500 million light-years across. It contains the mass of 100 quadrillion suns. On this rung, the Milky Way is just a tiny spark on one of the outer branches of a massive, glowing celestial tree. The ladder of scales has now taken us to a point where distance has become a concept that our brains can only process through mathematics. But there is one more rung we've discovered recently, the rung of the great filaments. These are the largest structures ever found in the universe. We are talking about things like the Hercules Corona Borealis Great Wall. This is a filament of galaxies that spans 10 billion light-years. That is about 10% of the entire observable universe. It is a structure so gargantuan that it challenges our fundamental understanding of how the universe began. According to the cosmological principle, the universe should be smooth and uniform on such large scales, yet here is a wall of matter that defies that smoothness. On this final rung, we aren't just looking at stars or galaxies, we are looking at the cosmic web, the very skeleton of reality. Think back to where we started, a 5-kilometer walk to the horizon. We have climbed from that walk to a structure 10 billion light-years long. The ratio between a human stride and the Great Wall is almost too large to write down in zeros. This is the ladder of scales. It is a journey of systematic humiliation for the human ego, but it is also a journey of profound discovery. Every time we move up a rung, we lose something and we gain something. We lose the feeling of being the center of the universe. We lose the idea that our planet is a massive, indestructible fortress. But we gain a perspective that no other known species possesses. We gain the ability to see the long view. We learn that the universe isn't just a place where things happen. It is a structured, evolving, and terrifyingly beautiful hierarchy. This ladder also teaches us about the nature of size. Size is entirely contextual. To a mountain, a human is nothing. To the earth, a mountain is a wrinkle. To the sun, the earth is a pebble. To the galaxy, the sun is a grain of sand. And to the cosmic web, the galaxy is a puff of smoke. When we talk about the largest object ever found, like the Quipu or IC 1101, we aren't just talking about big things. We are talking about the limits of structure itself. We are asking, how much matter can gravity hold together before the expansion of the universe pulls it apart? As you use this segment in your stories, remember that the ladder of scales is the ultimate narrative tool. It allows you to move the audience from the intimate to the infinite. It reminds the viewer that while their problems feel world-sized, the world itself is speck-sized. This contrast is where the awe comes from. It's the tension between our tiny, fragile lives and the massive, ancient structures that surround us. We are creatures of the first rung, yet we have built telescopes and theories that allow us to see the top of the ladder. We may never physically leave our neighborhood, but mentally, we have already conquered the Great Wall. We have mapped the Laniakea supercluster from the surface of a small, rocky planet orbiting an ordinary star. So, when you look at the night sky, try to see the rungs. Don't just see points of light. See the depth. Unmer. See the moon just above us, the planets further out, the stars beyond them, and the faint glow of distant galaxies beyond those. Understand that you are standing on the bottom step of a ladder that goes on forever. The horizon isn't 5 kilometers away, it's 46 billion light years away in every direction. And the fact that you can even conceive of that distance means that while you are physically small, your mind is as vast as the ladder itself. We have seen the scale. We have felt the shrink. Now, in the next segments, we will look at the bridge that connects these rungs, light itself. We will see how we cross these distances not with rockets, but with our eyes. The ladder is tall, but the view from the top is spectacular. To climb this ladder of scales is to participate in a systematic dismantling of our own intuition. We start with the Earth, our human anchor, where the horizon is a mere 5 kilometers away. On this first rung, we are masters of our domain. We measure the world in footsteps and hours. But the moment we look up and contemplate the lunar gap, that 384,400 kilometer chasm, we realize that our biological yardsticks are already starting to snap. If you were to drive a car at highway speeds toward the moon, it would take you 6 months of non-stop travel. If you chose to walk, you would need 9 years of your life. Already, on just the second rung of the ladder, the human scale has become a burden rather than a tool. As we ascend to the solar anchor, the numbers don't just grow, they transform. The Sun is 150 million kilometers away, 1 astronomical unit, AU. To walk this distance would take 3,500 years. We are now dealing with scales where entire civilizations could rise and fall in the time it takes to cross the gap. This is why we must transition to the most fundamental constant in the universe: light. Light is the only thing fast enough to act as a bridge across these gulfs. It travels at 300,000 kilometers per second. It can circle the Earth 7 times in a single heartbeat. Yet, even light takes 8 minutes to reach us from the Sunday. When we look at the Sun, we are not seeing it as it is now, but as it was nearly 9 minutes ago. We have begun our transition from space travelers to time travelers. The ladder takes us further into the interstellar neighborhood. Here, the Sun, a star that could hold 1 million Earths, shrinks into a tiny, flickering point of light among billions of others. We find ourselves in the Milky Way, a barred spiral galaxy, 100,000 light-years across. To grasp this, imagine the entire Earth is the size of a single grain of sand. In this scale, the Milky Way would be the size of the entire United States. Every star you see in the night sky is just a local neighbor in our small corner of this vast continental structure. We are tucked away in the Orion Arm, 26,000 light-years from a supermassive black hole that anchors our galaxy. On this rung, the individual planets are no longer visible. They are ghosts lost in the glare of 200 billion suns. But the ladder does not end at the edge of our galaxy. We reach the rung of the local group, a collection of 50 galaxies bound together by gravity. Our sister galaxy, Andromeda, sits 2.5 million light-years away. If the Milky Way is a city of light, the local group is a small cluster of towns separated by vast, dark countrysides. Beyond this lies the Virgo supercluster, a massive assembly of thousands of galaxies. And beyond that, the Laniakea supercluster, a structure so gargantuan it spans 500 million light-years. Laniakea, meaning immeasurable heaven, is a web of light where galaxies flow like water toward a gravitational center called the Great Attractor. As we reach the highest rungs, we encounter the defiant anomalies, structures that shouldn't exist. We find the Hercules Corona Borealis Great Wall, a filament of galaxies spanning 10 billion light-years. This structure represents 10% of the entire observable universe. Its very existence challenges the cosmological principle, which assumes the universe should be smooth and uniform on large scales. This wall is a giant knot in the fabric of space-time, a testament to the fact that the ladder of scales still has rungs we don't fully understand. We see giant circles in the cosmic microwave background and cold spots that hint at collisions with other universes or remnants from before the Big Bang itself. We also witness the monster galaxies like IC 1101. While our Milky Way is 100,000 light-years wide, IC 1101 is 6 million light-years across. It is an elliptical giant that has grown by devouring thousands of smaller galaxies over billions of years. If you placed IC 1101 where the Milky Way is today, it would swallow up Andromeda and most of our local group. It is a graveyard of stars, a terminal point in the evolution of galactic structures. At this scale, even the light that bridges the rungs takes millions of years to cross from one side of a single galaxy to the other. The ladder of scales reveals a universe that is a system of systems. Atoms form molecules. Molecules form dust. Dust forms planets. Planets orbit stars. Stars cluster into galaxies. And galaxies weave into the cosmic web. When we think about a galactic collision, we often imagine it in human terms. We think of cars bumping in a parking lot, or two marbles clinking together on a wooden floor. We measure time in minutes or years, and distance in miles we can drive. But to understand what is coming for the Milky Way, we have to scale our perspective. Imagine you are standing in a very large, silent field at night. If you take one single step, that step represents about 100 years of a human life. To reach the beginning of the Roman Empire, you'd only need to walk about 20 steps. To reach the end of the last ice age, you might walk for a minute. But to reach the moment Andromeda and the Milky Way finally touch, you would have to walk across that field, out of the gate, across the continent, and halfway around the world. Right now, Andromeda is about 2.5 million light-years away. It's moving toward us at about 250,000 miles per hour. That sounds fast. It's much faster than a jet or a bullet, but because space is so large, it's like watching a snail crawl toward a house from 3 states away. It is a slow-motion fall. This comparison isn't perfect, as the scale of stars is much thinner than the scale of snails, but it gives us a calm place to begin. The collision isn't a crash, it's a dance. And tonight, we are going to watch the first steps. To understand the distance of 2.5 million light-years, we must first think about the light itself. Light is the fastest thing we know, yet even light, traveling at 186,000 miles every single second, takes 2.5 million years to reach us from Andromeda. When you look at that faint smudge in the constellation of Andromeda tonight, you are not seeing the galaxy as it is now. You are seeing it as it was when our ancestors were first beginning to walk upright on the African savanna. You are looking at ancient history, delivered to your eyes on a beam of light that has been traveling through the freezing vacuum of space for longer than our species has had names for the stars. Imagine, for a moment, that we could shrink the entire Milky Way down to the size of a dinner plate. In this scale, the Sun would be a microscopic speck of dust, and the nearest star, Proxima Centauri, would be another speck about 4 miles away. Even at this tiny scale, the distance between the two galaxies is immense. If the Milky Way is a plate on a table in your kitchen, Andromeda is another plate sitting in a house several blocks down the street. Between those two plates lies nothing but cold, quiet air. They are drifting toward each other, but the movement is so subtle that if you stood and watched them for your entire life, you wouldn't see them move a fraction of a millimeter. We measure our lives in heartbeats, in hours, and in decades. We think of a long journey as a flight across an ocean or a drive across a continent, but the cosmos measures things in eons. To a galaxy, 1 billion years is like a season. The 250,000 miles per hour that Andromeda is traveling seems significant to us because we compare it to a car on a highway or a plane in the sky. But in the context of the 15 quintillion miles it has to travel, that speed is almost standing still. It is a patient approach. It is the steady, inevitable pull of two massive objects that have been aware of each other's gravity since the universe was young. When we use the word collision, our minds often jump to images of impact, shattering glass, the crunch of metal, a sudden and violent stop. But a galactic collision is nothing like that. It is more like two clouds of smoke drifting through one another in a still room. The stars within the Milky Way and Andromeda are so far apart that they will likely never touch. If you were standing on a planet orbiting a star in the middle of this merger, you might not even realize it was happening. You would simply notice that, over the course of many generations, the night sky was becoming more crowded, more luminous, and more beautiful. Think of a large, empty ballroom. If you put two people in that room and asked them to walk toward each other with their eyes closed, the chances of them bumping into each other are very small. Now, imagine that ballroom is the size of the entire Earth, and those two people are the only two things in it. That is the density of stars in a galaxy. They are lonely travelers, separated by such vast gulfs of nothingness that even when their galaxies merge, the stars themselves remain solitary. They pass like ships in the night, influenced by each other's gravity, changing their courses slightly, but never making contact. This perspective allows us to let go of the urgency we often feel when we hear about cosmic events. We are taught to think of the universe as a place of high-energy explosions and dramatic endings. But for the most part, the universe is a place of profound stillness and very slow movement. The dance between our galaxy and Andromeda has been going on for billions of years, and it will continue for billions more. It is a process that began long before the first cell divided on Earth, and it will reach its climax long after the sun has lived out its life. As you lie there, consider the weight of this time. There is a deep, structural peace in knowing that some things are so large they cannot be rushed. The Milky Way is not just a collection of stars. It is our home, a vast, spinning city of light. And Andromeda is our neighbor, a mirror image of our own home, slowly making its way across the dark to meet us. There is no friction in this movement. There is no noise. There is only the silent, mathematical perfection of gravity drawing two giants together. Astronomers have spent decades calculating the exact trajectory of this encounter. They use mathematics to peer into the future, just as they use telescopes to peer into the past. What they see is not a catastrophe, but a transformation. The two spirals will eventually lose their shape. Their arms will stretch out like long, glowing ribbons, pulled by the tidal forces of the interaction. These tidal tails will contain millions of stars, flung out into the void like seeds scattered by a gentle wind. Some of these stars may find themselves in new orbits, while others may be sent on a journey into the empty space between clusters, becoming wanderers in the dark. But even these exiled stars are part of the continuity. Nothing is truly lost. It is only rearranged. The energy that moves the galaxies is the same energy that moves the atoms in your room. It is a singular, connected system. As we move through this script, we will continue to zoom out, leaving the human scale behind and entering the realm of the truly cosmic. But for now, hold on to this image: the snail crawling toward the house, the plates on the table, the slow motion fall. The universe is not in a hurry to reach the end of its story, and you don't need to be either. Every breath you take is a small moment in a much larger timeline. The sky above us is changing, but it is changing so slowly that it feels like a promise of permanence. We are safe in the now, watching the forever unfold at its own pace. The first steps of the dance have already been taken. The music is the low, thrumming vibration of the vacuum, and the floor is the infinite stretch of space. We are simply here to witness the beginning of the merger. The universe is not in a hurry to reach the end of its story, and you don't need to be either. Every breath you take is a small moment in a much larger timeline. The sky above us is changing, but it is changing so slowly that it feels like a promise of permanence. We are safe in the now, watching the forever unfold at its own pace. The first steps of the dance have already been taken. The music is the low, thrumming vibration of the vacuum, and the floor is the infinite stretch of space. We are simply here to witness the beginning of the merger. To truly grasp the patience of this process, we must look at the way gravity handles its treasures. On a human scale, if you drop a glass, it shatters in a fraction of a second. Gravity acts with a sharp, uncompromising speed. But on a galactic scale, gravity acts more like a long, slow inhalation. It is a soft, persistent pull that takes millions of years to even register a change in position. Right now, as you rest, the Milky Way and Andromeda are leaning toward each other. It is a leaning that began before the first dinosaurs walked the Earth, and it is a leaning that will continue long after the last of our monuments has turned to dust. Imagine a vast, dark ocean. Two massive ships are miles apart, engines off, drifting only by the subtle tug of the tides. From the deck of one ship, the other looks like a stationary point on the horizon. You could watch it for a day, a week, a year, and it would never seem to get closer. But the tide is patient. The distance is closing. This is the pace of the cosmic now. It is a scale of time that is so generous. It allows for the rise and fall of entire biological eras within a single inch of galactic movement. When we say we are safe in the now, we are acknowledging that the cosmic timeline provides a profound buffer against the chaos of the immediate. The forever that is unfolding is so vast that it cushions every moment of our lives. The sky you see tonight is, for all intents and purposes, the same sky that will be seen by the next 10 generations. The constellations Orion, Cassiopeia, the Great Bear are like ancient landmarks on a map that is being redrawn so slowly the ink takes millions of years to dry. This slow-motion reality is a form of protection. It ensures that the foundations of our world, the stars, the sun, the relative position of our galaxy, are effectively permanent on the scale of a human life. Scientists understand this permanence by calculating the proper motion of stars. Even the fastest moving stars in our neighborhood take thousands of years to move a distance equal to the width of the moon in our sky. To us, they are fixed points. To the universe, they are vibrating slightly, shifting and settling as they respond to the gravitational deep tissue massage of the approaching Andromeda. This comparison isn't perfect, as stars don't have feelings, but it helps us visualize the relaxation of the cosmos. The universe is not a rigid structure. It is a fluid, evolving system that moves with the grace of a cloud shifting in a summer breeze. Consider the thrumming vibration of the vacuum. We often think of space as a silent, empty void, but in the language of physics, it is a field of potential. It is the floor upon which the galaxies dance. Every atom in your body is connected to that floor. When we talk about the merger of the Milky Way and Andromeda, we are talking about a restructuring of the floor itself. The geometry of space is being warped and stretched, creating the paths that the stars will eventually follow. It is a silent, mathematical music. You don't need to hear it to feel its influence. You simply need to exist within it. Think about the first steps of this dance. In a ballroom, the first step is often the most deliberate: a bow, a meeting of eyes, a slow movement toward the center of the floor. Andromeda and the Milky Way have already finished their bow. They have been locked in each other's gaze for billions of years. Now, they are in the phase of the approach. They are moving through the intergalactic medium, clearing a path through the thin, warm, hot gas we discussed. This movement is so smooth that there is no friction, no heat, and no noise. It is the ultimate expression of effortless motion. As you lie there, let your own movements become just as effortless. Your breath is its own kind of dance, a rhythmic expansion and contraction that mirrors the cycles of the stars. You are a small, quiet participant in the merger. Your atoms, which were once part of a star that lived and died long ago, are now part of a being that is witnessing the next great chapter of that star's history. There is a deep, structural continuity in this. You are not an outsider looking in. You are a piece of the galaxy contemplating its own future. The forever that is unfolding does not require your permission or your energy. It is an inevitable process, driven by the same laws that make a leaf fall to the ground or a planet orbit a sun. This inevitability is a source of peace. In a world where so many things are uncertain, the merger of the galaxies is a mathematical certainty. It is a promise kept by the universe. It reminds us that there is an order to things, a grand architecture that remains stable even when our individual lives feel chaotic. Astronomers didn't always realize that the now was so stable. In the early days of cosmology, there was a fear that the universe might be a place of sudden, violent collapses. But the more we look, the more we see the patience. We see that the final hour is actually a final eon. We see that the collision is a merger. The language we use to describe these events has softened as our understanding has grown. We no longer see a catastrophe. We see a union. We see the birth of Milkomeda, a single, massive, peaceful island of light. This shift in perspective is what allows the mind to relax. When we replace the shocking with the inevitable, the brain stops looking for threats and starts looking for patterns. The pattern of the galactic merger is one of beauty and symmetry. It is the two-part harmony of gravity. As the Milky Way and Andromeda draw closer, they will begin to pull on each other's edges, creating the long, glowing tidal tails we will explore later. But for now, they are still two distinct entities, moving toward each other with a respect and a grace that only the cosmos can achieve. Imagine the floor of the infinite stretch of space. It is a velvet darkness that stretches in every direction, dotted with the light of 1 trillion suns. Upon this floor, the two galaxies are moving at 250,000 miles per hour, yet they seem to be standing still. This is the paradox of the human scale perspective. We can know the numbers, but we can only feel the stillness. That stillness is where we live. That stillness is the now that protects us. Every breath you take is a small moment in this timeline. If you lived for 100 years, you would take about 800 million breaths. In that same time, Andromeda would have moved about 200 billion miles closer to us. That sounds like a lot, but on the scale of 15 quintillion miles, it is almost nothing. It is like the snail moving another fraction of an inch toward the house 3 states away. The snail is not tired. The snail is not in a hurry. The snail is simply moving because that is what it does. The universe is simply moving because that is what it does. It is expanding, it is pulling, and it is merging. You can let go of the need to keep up. You can let go of the need to understand every mile of the 15 quintillion miles. You are here, in the kitchen of the universe, and the plate on the table is perfectly still. The partner plate is blocks away, and the walk toward each other is the longest, slowest, most beautiful walk ever taken. As the night deepens, let the thrumming vibration of the vacuum become the white noise of your sleep. It is the sound of existence itself, the low-frequency hum of a universe that is working exactly as it should. There are no alarms in the deep field of space. There are no sudden twists in the orbits of the stars. There is only the steady, unhurried progression of gravity. We are safe in the now. The sky is a promise. The dance is beginning, and you are here to witness it, not with the urgency of a scientist, but with the quiet wonder of a passenger. You are on a journey that will take billions of years, and you have already arrived. You are exactly where you need to be, resting in the arms of a galaxy that is falling into the arms of another. The music is playing, the floor is vast, and the dance is a slow-motion fall into the future. There is no rush. The universe is patient, and tonight you can be patient too. You can allow the forever to unfold while you rest. You can allow the now to be enough. The first steps have been taken. The rest of the dance will wait for you. The observations of K-18b continue, a series of data points stretching into the coming years. Each transit of the planet across its star is another opportunity to listen to the chemical signature. The golden mirrors of the James Webb Space Telescope remain aligned, capturing the infrared whispers of the distant atmosphere. We are gathering more information, bit by bit, layer by layer. The search for dimethyl sulfide will continue, a quiet quest for a biological hint in a sea of chemistry. The scientists in their offices and the telescope in its orbit are part of the same steady process. There is no final answer, only a deepening of the mystery. The planet remains in its 33-day loop, a constant presence in the constellation of Leo. The light travels, the sensors record, and the computers process. The cycle of discovery is as rhythmic as the orbit itself. We find ourselves moving from one question to the next, a slow progression toward a horizon that always stays just out of reach. The ocean of K-18b remains dark and deep under its thick hydrogen sky. The waves move in the dim red light, driven by internal heat and the gravitational pull of the dwarf star. It is a world of constant, heavy pressure and eternal twilight. We can imagine the stillness of those depths, a place where time moves differently. The atmosphere above holds its secrets, releasing them only in tiny fragments of light. We accept these fragments with gratitude, building a picture of a world we will never touch. The data flows in a continuous stream, a digital river connecting us to the Haitian world. There is no sense of an ending, only a sense of ongoingness. The telescope will eventually look at another star, another planet, another mystery, but the story of K-18b will remain in the archives, a permanent record of our curiosity. The stars do not stop burning when we stop looking. The planets do not stop orbiting when we go to sleep. The universe continues its slow, magnificent work, indifferent to our schedules and our clocks. We are simply part of the flow, a quiet presence in the infinite. The light is still coming, the data is still forming, the world is still there, spinning in the dark, waiting for the next transit, the next measurement, the next moment of silent understanding. This process of becoming and being is a permanent fixture of the deep dark. It does not require our attention to persist. As you drift toward the edges of thought, consider the permanence of the K-18 system, a place where the laws of physics are the only governing body. There is no urgency in the way the hydrogen settles in that distant sky. There is no haste in the way the red dwarf star converts its fuel into the soft, crimson glow that has traveled across the void to find us. Everything is happening exactly as it must, at a pace that defies our human need for speed. You are part of a continuity that transcends your own timeline. The atoms that once swirled in the protoplanetary disk of K-18 are the cousins of the atoms that now rest in your own hands. We are connected by a shared ancestry of stellar death and rebirth. When a star reaches the end of its life, it breathes its heavy elements back into the cosmos, providing the seeds for future worlds, future oceans, and future skies. K-18b is a recipient of this ancient inheritance, just as Earth is. We are siblings in the chemical sense, sharing a lineage that reaches back to the first generation of stars. This realization allows for a profound sense of belonging. You are not a stranger in the universe. You are a native of the vastness, looking out at another corner of your own home. We think of the future missions that will follow the James Webb. We think of the telescopes that will be able to see the surface of these oceans, or the probes that might one day in the far distant future dip their sensors into the alien water. These are the dreams of a species that is just beginning to find its way in the dark. But for now, we have the light. We have the spectroscopy. We have the quiet evidence of a world that is fundamentally different and strangely familiar. We find comfort in the data, a sense of grounding in the facts. The universe is not a place of chaos, but a place of order and beauty. The infinite ending is the realization that we are part of a system that is much larger than ourselves. We are the eyes of the universe, looking back at itself. We are the minds of the universe, trying to understand its own rules. This role is a privilege and a peace. It means we have a purpose in the dark, to see, to record, and to wonder. The world of K2-18b is a part of that purpose. It is a destination for our thoughts, a harbor for our imagination. It is a watery world in the constellation of Leo, a point of light that tells a story of oceans and hydrogen and the slow, steady progress of time. As you drift further away from the specifics and toward the absolute calm, let the scale of the universe carry you. You are part of the spiral arms of the Milky Way. You are part of the expansion of space. You are part of the continuity of matter. The planets do not stop. The light does not stop. The work of the cosmos is never finished, and that is its greatest beauty. It is a story with no last chapter, a mystery with no final reveal. It is an infinite drift through the deep, quiet, dark. The methane stays in the sky, the water stays in the sea, the star stays in its place, and you remain in yours, a quiet observer of the magnificent work. The light is still coming. The data is still forming. The world is still there, spinning in the dark, waiting for the next transit, the next measurement, the next moment of silent understanding. The drift is complete, and yet it is only beginning. The universe remains, indifferent to our schedules and our clocks, continuing its slow, magnificent work, forever and always, in the silent, velvet dark.